We talked last time, a week ago, about Lewis dot structures, and really it's a manifestation of the octet rule. And the octet rule is not a firm rule. There's exceptions to it. We're going to see exceptions to it. But the idea of the octet rule is for the main group elements, and that's groups 1A, 2A, the alkali metals, alkaline earths, and then groups 3A through 7A, the halogen 7A, oxygen group 6A, nitrogen group 5A, carbon group 4A. These main group elements, oftentimes we can justify the compounds that they form based on their wanting to have an octet of electrons in their valence shell. And obviously the noble gases, except for helium, the noble gases already have an octet. And that's why in nature, the noble gases don't generally form compounds. Now they've made some compounds out of xenon in the lab, but in nature, the noble gases pretty much just exist as individual atoms, and they already have an octet in their valence shell. They're very stable, and that's why they don't form compounds. But the octet rule, and again, there's exceptions to it, but for the main group elements, they either gain, lose, or share electrons to have 8 electrons in their valence shell. And simple examples, the Lewis dot structures that we were discussing, these were before quantum mechanics. This is before electron configurations and so on. And they don't really have anything to do with the actual shapes of molecules per se. They're just electron bookkeeping to try to justify why certain compounds are formed from certain main group elements. And sometimes it's simple examples, and for the nonmetals, as you know, group 7A, the halogens, typically have one covalent bond. 6A, the oxygen group, 2. 5A, nitrogen group, form 3 covalent bonds. Carbon and silicon, 4. And you can see the number of valence electrons plus the number of bonds they form add up to 8. The halogens have 7 valence electrons. If they form a covalent bond and they borrow an electron from another atom, it's as if they have an octet in their valence shell. When oxygen forms 2 bonds, when nitrogen forms 3, when carbon forms 4. So simple Lewis dot structures, and let's just use carbon, which has 4 valence electrons, nitrogen, which has 5, oxygen, which has 6, and we'll just pick a fluorine, which has 7. If we look at the compounds of these nonmetals with hydrogen as an example, we can see the octet rule. These are straightforward examples, very simple examples. For a carbon, it wants to form 4 bonds, and so if we have 4 hydrogens, we have the compound methane, of course. And if you look here, you can see around the carbon, there are 8 valence electrons. So by forming 4 covalent bonds, carbon now has 8 instead of 4 valence electrons. And we can also write it like this, can't we? Now obviously hydrogen doesn't have an octet. It has 2 electrons now, just like the noble gas neon. Well, here's nitrogen. If we look at the compound that's formed with hydrogen, we'll have ammonia, and we'll have 3 hydrogens here, and we have what's called a non-bonded pair. Notice now the nitrogen has 8 electrons around it, and so it has an octet, or we could draw it like this, can't we? But when we draw the Lewis dot structure, we also have to include that non-bonded pair. Again, these bonds, these pairs of electrons, have nothing to do with the 3-dimensional shape of the molecule. We're just doing a sort of electron bookkeeping to justify why these stable molecules exist. Oxygen has 6 valence electrons, we'll do it up here first. If we have a hydrogen here and a hydrogen here, now the oxygen has an octet, and of course that's a water molecule. And so we can also draw it like this. This is not the shape of water, it's not bent, it's actually bent. That's a totally different issue, is what its 3-dimensional shape is. This is just its Lewis dot structure. And then hydrogen and fluorine form the compound hydrogen fluoride. And we can draw it like this. Wherever you see a covalent bond, that's 2 electrons being shared by both atoms. 2, 4, 6, 8. 2, 4, 6, 8 around the oxygen. 2, 4, 6, 8 around the nitrogen. 2, 4, 6, 8 around the carbon. The carbon has no non-bonded pairs. Nitrogen has 1. Oxygen has 2. Fluorine has 3. Again, this is old stuff. It's before that we learned about s orbitals and p orbitals and electron configurations. Well, now we're going to see that there are exceptions to the octet rule, but we literally can draw millions of molecules that satisfy the octet rule and justify the number of bonds involved. But we're going to see also that there are exceptions to the octet rule. When you get on this, when you get below carbon, nitrogen, oxygen in the main group elements, when you encounter sulfur and phosphorus, they have an ability to expand their valence shell. And they can make compounds that don't follow the octet rule. They might have 10 electrons in their valence shell. Also, there's beryllium, which can have 4 instead of 8, and boron, which can have compounds where it has 6 valence electrons instead of 8. So there's exceptions to the octet rule, but again, we can still use it to justify literally millions of compounds. Now, another topic in this this chapter, and one thing, if you look carefully at the slides in this, the PowerPoint for this chapter, or the book, you'll see that there's times that it gets difficult to draw the Lewis dot structures. There are, again, exceptions all over the place. There's unusual molecules. We'll look at a few of those. Now, what about double and triple bonds? Well, we use carbon as an example. Let's say carbon has a double bond, and this is ethene, or it's got the trivial name ethylene. But and this also, of course, satisfies the octet rule for both carbons, because a double bond counts as 4. 2, 4, 6, 8 around this carbon, 2, 4, 6, 8 around this carbon. How would you write the Lewis dot structure for that? Well, you have to put 2 pairs of dots for a double bond between the carbons, and then you have 2 bonds to hydrogen here, 2 bonds to hydrogen here. And so now there's an octet around the carbon here, and there's an octet around the carbon here. So that was how you would draw a Lewis dot structure of a carbon carbon double bond. If you have a carbon-carbon triple bond, well, it counts as if it's 3 bonds. And so you have 2, 4, 6 electrons being shared here. And if we draw the Lewis dot structure, it's going to be like this. There's 8 electrons around the carbon here, 8 around the carbon here. Are the number of electrons correct? Well, let's think about it for both of these molecules. We have 2 carbons with 4 electrons here, and then we have a total of 4 hydrogens. So as far as electron bookkeeping, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 valence electrons here. And if we count here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay? For acetylene or ethine, we have 2 carbons, 1, 2, 3, 4, 1, 2, 3, 4, and 2 hydrogens, 1, 2. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 total electrons here. And we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 here. Okay. The next topic they look at here is now is called formal charge. And formal charge, one way to look at it is that, especially when you have a molecule where there's an atom of a main group element that's forming a different number of covalent bonds than what it does typically. I mentioned there's exceptions to a lot of this stuff. And a more formal definitions here, let's read it. An atom's formal charge is the difference between the number of valence electrons in an isolated atom and the number of electrons assigned to that atom in a Lewis structure. Okay, and the equation is actually quite simple. The formal charge on a certain atom in a molecule, you're looking at that atom in the molecule, and its formal charge is the total number of valence electrons if you have the free atom. And you can get that right off the periodic table, can't you? Like if you're looking at a carbon, it's in group 4A, you know it started out with 4 valence electrons. And then you subtract the total number of non-bonding electrons, and then you subtract 1/2 times the total number of bonding electrons. Don't forget there's 2 electrons in each covalent bond. And if a nonmetal is behaving normally, or the way we usually see it or predict it, its formal charge is 0. But there's times that there are molecules and ions that are formed that are not typical. Well, let's pick an example. Here is a molecule of ammonia. And here it's behaving normally. The nitrogen has 3 bonds, that's which we predict. It's got 1 non-bonded pair, and it has an octet. Typically, this is what nitrogen would do, and now we're going to look at some exceptions to what it does typically. In this direction, let's suppose it gets a hydrogen ion or proton. Chemists say, let's suppose this pair of electrons forms a bond to a proton, and chemists refer to that as the nitrogen gets protonated. Well, when you do that, if you add this ammonia plus this hydrogen ion, this whole species has a plus charge, and it's called ammonia. And we're going to look and see the atom that's actually responsible for this positive charge on the ion. Notice the nitrogen's not behaving normally. It's got 4 single bonds and no non-bonded pairs, and yet this ion exists. Also, we're going to go through a series of in the other direction, we're going to deprotonate ammonia. Now this is a very reactive anion. It's called amide, and it has a -1 charge. Essentially, it lost a proton. You can't have this ion in water. It would just simply remove a proton from water and make ammonia again. If a chemist wants to make this very reactive ion, they have to do it in another solvent. It can't be in water. But again, I'm just using these as examples to show you the concept of formal charge. Here's another species that we might generate where the nitrogen only has 1 bond, and this has a -2 charge, and then let's say it loses another proton, and now we have, does anyone remember the name of this? This is just nitride. It's the ion that nitrogen forms. Okay? It's all by itself. Well, let's calculate the formal charge of the nitrogen in ammonia. Okay? If you have a nitrogen atom, it has 1, 2, 3, 4, 5 valence electrons. In the equation, the total number of valence electrons in the free atom, and so that would be 5 for nitrogen, wouldn't it? Anybody see that? Then minus the total number of non-bonding electrons. Well, there's 1 non-bonded pair, so there's -2. Okay? And then it's -1/2 times the total number of bonding electrons. Well, there's 2 in this covalent bond, 2 in this covalent bond, 2 in this covalent bond. That's a total of 6. So we're going to have 1/2 times 6. What's the answer to the formal charge? Just 5 -2 -1/2 of 6 is
0.
That's just 0. Okay, the formal charge of the nitrogen in ammonia here is 0. Well, I put some other examples up here where the formal charge of the nitrogen is not 0. This is the way we're used to seeing nitrogen. 3 bonds and a lone pair. But here we've got nitrogen that has 4 bonds and no lone pairs. So let's figure out the formal charge of this nitrogen. Well, again, how many valence electrons does a free nitrogen atom have?
0.
How many valence electrons does a free nitrogen have?
5.
It's right on the periodic table. It's in group 5A, okay? 5 minus. And next we have the total number of non-bonding electrons.
2.
0.
Yeah.
In this molecule, well, it's not a molecule, it's an ion. In this species, it's 0. You don't see any pairs of electrons not bonded to anything, do you? This is -0, okay? -1/2 times the number of bonding electrons. How many bonding electrons are there now?
4.
Don't forget each
8.
bond, there's 8. Okay, good. So 1/2 times 8. Well, 5 minus 0 is 5, minus 1/2, 8 is 4. The formal charge of that nitrogen right there is +1. Within that ion, that nitrogen actually is thought of as having a plus charge. And the reason it has a plus charge is it's not bonding in a typical way, is it? It doesn't have 3 bonds and a lone pair. It actually has 4 bonds and no lone pairs. Okay? What really happened and why it has a plus charge within that ion is one of its non-bonded pairs became part of the hydrogen that it's bonded to in a new covalent bond. It's kind of like I've loaned it to hydrogen. Well, this is not normal either. This is the M and anion. This is very reactive. You can't make it in water. You have to make it in an organic solid if for some reason you want to. But let's do the formal charge for that nitrogen. Well, how many valence electrons does nitrogen have? 5. Okay. Minus how many total non-bonding electrons?
2 or 4? 2.
1, 2, 3, 4. Okay. Minus 4. And then minus 1/2 times the number of bonding electrons.
4.
Okay. And what do you get? You get -1. That nitrogen in this ion has a formal charge of -1. And the reason is it picked up an electron from somewhere. I'll put it as an X. So it has an octet without having to form 3 bonds. Really what happened is it lost a proton. It lost a hydrogen ion. Okay? But suffice it to say that the nitrogen, and you have to realize the fact that that nitrogen has a formal charge of -1 is the reason the whole ion has a charge of -1, because these hydrogens are behaving normally. Hydrogen typically forms 1 bond, end of story. Okay? So we can say the reason this ion has a -1 charge is because the nitrogen within the ion has a -1 charge. Over here with ammonium, we can say that the entire ammonium ion is +1 because the nitrogen in the ammonium ion is +1. Okay? Now you can probably see the trend here, but what's the formal charge of nitrogen in this species? How many valence electrons?
5.
Okay, minus. What is my equation here?
6.
Okay, total number of non-bonding electrons is 6. Minus 1/2 of the bonding electrons is
2.
5 minus 6 is -1, and 1/2 of 2 is another -1. So you end up, that nitrogen has a formal charge of -2. Okay? Does everybody see that? Now we can calculate it for nitride, and the way nitride forms, it's a nitrogen atom that got 3 electrons from someone and has an octet. But that means it has a 3- charge. And we can calculate the formal charge, but it's kind of silly. It's not bonded to anything. So it's obviously got a -3 charge. But if we calculate it, we'd get -3. Okay? Does everyone see how the formal charge equation works? And you're looking at a certain atom in a molecule or an ion. Okay, when you calculate. Okay? So that's the notion of formal charge here. And here it gives you a variety of examples. And you can look at these at your leisure. And I think, Cassidy, you noticed that there are some practice problems with this next exam?
Yes.
So you may want to take a look at that. Now, another concept in this chapter is has to do with electron delocalization. There are times when molecules or ions where electrons actually are part of bonding in more than one bond. And these are where we come up with what are called resonance structures. Now, chemists draw resonance structures to try to rationalize or understand or explain the fact that electrons are sometimes involved in more than one bond. And I'll show you a few examples. And they've studied some of these molecules and ions. Some of them, they've studied them to death. One classical organic compound that's been studied to death as far as resonance is concerned is benzene. But oftentimes, the fact that we can draw more than one Lewis dot structure is related to the chemistry of the molecule or the ion. I'll give you one example of the concept of resonance, and this is the polyatomic ion that we call carbonate. And if we drew a Lewis dot structure for carbonate, I'll draw it both ways, but we can draw it like this. Or we could draw it like this. Either way, and this entire ion, if I put it in brackets, or this entire polyatomic ion that we call carbonate has a 2- charge. And if you use the equation that we just talked about for formal charge, I mean, just looking at this Lewis dot structure here, what atoms do you see that aren't behaving normally? I mean, based on our covalences that we talked about, we said that carbon forms 4 bonds, and nitrogen 3, and oxygen 2, etc. Do you see anything that's an exception to those covalences?
The oxygen.
These 2 oxygens here only have 1 bond, and oxygen usually has 2. So you would suspect that maybe the formal charge on those isn't 0. Of course, you can always calculate it with that simple equation. If you calculate it for carbonate, you'll find that the formal charge of the carbon is 0. It's behaving normally. It's got 4 bonds. One's a double bond, but this oxygen here has a formal charge of 0. It's got a double bond, which counts as 2, and it's got 2 pairs of electrons. But these oxygens here, if you calculate the formal charge for this oxygen, it would equal -1. And if you did the formal charge for this oxygen, it's equal to -1. And this is what gives the entire ion its charge of -2. Okay? But to compound things and to make things even more confusing, it's actually experimentally determined that all three of these carbon-oxygen bonds are the same length. And that's contradictory to what I drew here, because double bonds are usually shorter than single bonds. Okay? And this is an example of where this concept of resonance comes in. Because resonance structures by themselves don't necessarily exist. Resonance structures show the actual ion or molecule as an average of the likely resonance structures we can draw. And so I'm going to show you the resonance structures for carbonate. And there's three of them, and they're equivalent in energy, it turns out. Well, if we take this form of carbonate, and here's a pair of electrons, if it forms another bond here, and then one of these two bonds becomes a non-bonded pair here, then, and we draw kind of a double arrow here, now we've got something like this. And that's a second resonance structure for carbonate. Well, instead of the double bond being here, now it's down here. Well, we can do the same thing with this resonance structure. This oxygen, a pair of electrons can form a bond here. One of these two bonds will stay up as a non-bonded pair here. And we can draw a second, well, a third resonance structure. And you can see these are just three different Lewis dot structures. But the point of resonance is, and when chemists draw resonance structures like this, they're not suggesting that this is some sort of reversible process going back and forth. That's not the point. They draw them to justify the fact that each bond between the carbon and oxygen is really 1 1/3 bonds. Because they've done experiments and they show these bonds are all the same. And we can use these resonance structures to justify that this is really, okay? And then, of course, if you look at it from the standpoint of charge, instead of having two oxygens with a minus charge, don't forget it's got to add up to -2. So you got -1.5 charges as a so-called formal charge on each of these. No, I've got that wrong, don't I? It's too late. They have to add up to -2. So this is -2/3 here. This is -2/3 here. This is -2/3 here. You add them together, you get -6/3. That's -2. Sorry. So, but again, the charge is evenly distributed. This formal charge is evenly distributed on all three oxygens. Okay. Now here they're giving you an example here at this on this slide here of another. This is an actual molecule, and they have actually shown for you this oxygen's formal charge is +1, and this oxygen's formal charge is -1. Does anyone know what O3 is? The name of it? This form of oxygen?
Ozone.
It's ozone. And ozone is high in the atmosphere. It's formed by cosmic radiation from the sun, bombarding oxygen molecules in the atmosphere. It has the ability to absorb ultraviolet light and help prevent us from getting skin cancer on the ground. But it's also a pollutant in cities like Los Angeles. We want it high in the atmosphere. We don't necessarily want it in our cities. And it is using these two resonant structures. The actual Lewis dot structure, if you will, is halfway between these two structures. Ozone is also formed by lightning when it passes through the atmosphere. After a thunderstorm, you can kind of smell a sweet smell on the horizon. It's ozone. Or if you like to play with electric equipment and something sparks, you smell a funky little sweet smell. Might be a little ozone you made. Alrighty, now I mentioned benzene. We're not talking much about organic chemistry this semester, but benzene, the so-called Kekule structure for benzene, looks like something like this. Alternating single and double bonds in a ring. But again, chemists have done experiments, and we found that, for one, benzene doesn't undergo the same chemical reactions that carbon-carbon double bonds undergo. And secondly, we've discovered that all the bonds, carbon-carbon bonds, are the same length. Well, again, you can write a resonance structure, and chemists like to sometimes get rid of the hydrogens because they're a nuisance, and just draw a skeletal structure like this. But if we draw a resonance, we can have this bond flipping in here, this one flipping here, and this one flipping here, and the second resonance structure will look like this. And again, benzene's not considered to be either one of these. It's actually halfway between them. So it's as if there's 1.5 bonds between each pair of carbons. So that's another example of resonance. Now here it discusses, I told you there's going to be exceptions to the octet rule, and going to nonmetals with atomic numbers less than carbon. When you get over to beryllium, it can actually form molecules where the beryllium atom only has 2 bonds and no non-bonded pairs. And so it only has 4 valence electrons around it. It doesn't satisfy the octet rule, but the compound exists. Boron is another nonmetal on the periodic table that doesn't satisfy the octet rule. It makes stable compounds with 3 covalent bonds and no non-bonded pairs. And here's the example of boron trifluoride. And you can see that it only has covalent bonds 2 electrons. 3 times 2 is 6. It's only got 6 electrons around it. So beryllium and boron may make a variety of compounds that don't obey the octet rule. Odd electron. Now these are kind of interesting. Ask someone if they know the structure of nitrogen oxide, and if they say no, they get it right. But you have 1 nitrogen and 1 oxygen, and this doesn't make sense, does it? Now, how can nitrogen form 3 bonds and oxygen form 2? Well, it doesn't. This is a stable molecule, nitrogen oxide, but it's got an exception to the octet rule and actually has an unpaired electron, and this actually can be measured because it has magnetic properties. If you look at the oxygen, it has 2, 4, 6, 8 electrons around it, so it satisfies the octet rule. But the nitrogen has 2, 4, 6, 7. And they use this molecule for research because of the fact that this the spin state of this unpaired electron can be measured. I also told you, I think at the beginning of class, but when you get on the next period of the periodic table below carbon, nitrogen, oxygen, sulfur and phosphorus can both expand their valence shell, and here's an example of that. Here, sulfur hexafluoride, obviously, it doesn't have an octet around it, does it? Now these fluorines all have an octet, but they're behaving normally and forming one covalent bond. But the sulfur has 2, 4, 6 times 2 is 12. 12 valence electrons around the sulfur. And yet this is a stable compound, and it's another exception to the so-called octet rule. But again, there are millions of compounds that satisfy the so-called octet rule. But then there's also exceptions. Alrighty, we saw this before as an extra credit question on one of the exams, but chemists often want to know the bond energy of a covalent bond, and they do experiments to measure these values. And here it's showing you the bond energy is literally, if you have a molecule, it's literally the energy required to break a covalent bond. Now, here's hydrogen, for example. It has one single bond, and you can see it's got a positive enthalpy. It takes energy. It's endothermic. It takes energy to break that covalent bond and make two hydrogen atoms. And these two hydrogen atoms won't remain as atoms. I mean, if you turn off the heat source or what have you, they'll re-establish the covalent bond and form the molecule again. But they have experimental techniques for determining these bond energies. When you have an atom like hydrogen or chlorine or any nonmetal that usually has a covalent bond to something, and you make the free atom, we call those free atoms free radicals. They're extremely reactive, and they're not going to stay that way unless they try to make stable free radicals in research sometimes at low temperatures, but if allowed to, they'll reform the covalent bonds that they had to begin with simply because they're more stable that way. But you can measure the energy of breaking covalent bonds of different types, and here you can see enthalpies for these things. Notice that we think of oxygen, at least right now, until we learn that it's wrong, we think of oxygen as having a double bond when we have oxygen gas. And it takes more energy to break a double bond than a single bond. And then nitrogen especially, it's got a triple bond, and look how high its bond enthalpy is. It takes even more energy to break a triple bond than a double bond. And here are some typical or average bond energies for a variety of different kinds of covalent bonds. One thing, just to kind of give you some feel for this, but if you were trying to determine the bond energy of the carbon-hydrogen bonds that are in methane, for example, well, they would do experiments and they'd figure out how much energy it takes to break one of these bonds. And that maybe would be enthalpy 1 here. And then they determine how much energy it takes to break another one. And and that would be enthalpy 2 perhaps. And they do it again, enthalpy 3, and again, and to have a free carbon atom, this would be maybe enthalpy 4. And when they publish the actual bond energy, it's the average of these 4. And so it would just be, you know, delta H1 plus delta H2 plus delta H3 plus delta H4 divided by 4. And they refer to that as the average carbon-hydrogen bond energy in methane, for example. But they differ in value. It becomes more difficult to remove each of them. So here, here is an example with water. I mean, you've got one oxygen-hydrogen bond broken, and you measure its enthalpy, and then you break the other one and measure its enthalpy and average them, and then you can say the average oxygen-hydrogen bond energy or bond enthalpy is the average of those two. Now, because of, I'm trying to find an equation for it.
That's good. Thank you. Thank you.
When you know bond energies, you can use bond energies to figure out the energy of a reaction. Here's an example. Let me see, where does this problem start? Here's an example problem, and it's a little bit busy, but let's think about it and think about Hess's laws, not so much to solve the problem, but just to think about it. If you have the reaction of hydrogen gas with oxygen gas to make water, and you want to, and this I'm sure is in the literature, the heat of the reaction, but if you wanted to use bond energies to try to approximate the heat of this reaction, if you think about it, energy is going to be consumed to break the hydrogen bond and the oxygen bond, so that's the energy investment. And then energy is actually going to be liberated when oxygen-hydrogen bonds are formed. And so here they're kind of tabulating this based on the bond energies of hydrogen, hydrogen, oxygen, oxygen, and oxygen, hydrogen. You can approximate or determine approximately the heat of the reaction based on what bonds are formed and which bonds are broken. And that's what this problem is all about. Okay. All right, well, we survived this. As before, you want to make sure you look at the study guide. The book, for some reason, in the next chapter we're going to talk about, I don't want that. They put a lot of material into chapter 10. Well, let's kind of see if we can kind of review what we talked about from this chapter. And again, but some of this is qualitative or definition or whatever, but, and some of it's review. Now, ionic compounds obviously are formed when metals that have lost electrons to form cations and nonmetals that have gained electrons to form anions. Covalent compounds, and we learned this at the beginning of the semester, have covalent bonds, and they typically involve two nonmetals. We know for the main group representative elements, it's easy to know how many valence electrons they have because it's the same as their group number on the periodic table. The alkali metals 1A have 1 valence electron. The alkaline earth group 2A have 2 valence electrons. Oxygen's in group 6A, it has 6 valence electrons. We talked a little bit more today about Lewis dot structures. If you're drawing the Lewis dot structure of an atom of an element, well, you need to know how many valence electrons it has before you draw the dots. And then we put atoms together. We showed examples of making molecules and ions and showing their Lewis dot structure. And there's practice problems that are probably simpler than the examples they give you in these PowerPoints. Non-polar covalent, polar covalent, and ionic bonds. If you have two main group elements, or if you have the electronegativity for any metal, for that matter, you can predict if the bond is ionic, polar covalent, or non-polar covalent simply by subtracting their electronegativities. And if the electronegativities of the two atoms are very, very, very close, if the difference is very close to zero, you're going to have a pretty pure covalent bond. And there's guidelines on that, what constitutes non-polar covalent, polar covalent, and ionic. When you have a metal and a non-metal like fluorine, the difference in electronegativity is substantial, so you know for sure that those two elements are going to form an ionic bond and an ionic compound. We talked today and looked at examples of calculating the simple parameter we call formal charge. Also, this is qualitative. Elements that can form an expanded octet. The octet can be expanded by some elements by utilizing d orbitals found in the third principal energy level and beyond. So examples of elements that can expand their valence shell are sulfur, phosphorus, silicon, and chlorine. And then other exceptions to the octet rule we looked at, compounds of beryllium and compounds of boron. They have fewer than an octet. And then another exception to the octet rule is odd electron compounds of nitrogen and oxygen. And that's kind of all there is to that. In the blackboard here, next week we want to start looking at the practice problems for exam 5. And hopefully some of these are straightforward. Number 1, draw the Lewis dot structure for aluminum, oxygen, lead, chlorine, and calcium. And you just look at their group number to see how many valence electrons they have. Aluminum is in group 3A. You put 3 dots around it. Simple. Okay. Draw the Lewis dot structures for oxide. Well, that's the ion that oxygen forms. So an oxygen atom has 6 valence electrons. If it gains 2 more electrons, it has a -2 charge. It has an octet. So the Lewis dot structure is just oxygen with 8 electrons around it, but it has a -2 charge. Nitride also has an octet and a -3 charge. Sulfide has an octet, a -2 charge. Fluoride, if it gains 1 electron, has an octet, a -1 charge. Hydride, when the hydrogen atom gains another electron, it has a -1 charge. It doesn't have an octet, it has 2 electrons, just like helium. Using the rules on the difference in electronegativity to determine that the following binary substances have a non-polar covalent, polar covalent, or ionic bond. We expect metal, non-metal to be ionic. We have a metal, non-metal here and here, but go ahead and look at the table of electronegativities and subtract it and see how much it is. Also, we expect whatever nitrogen's electronegativity is, when it bonds to itself, well, both of them have the same electronegativity, the difference is 0, and you're going to have a non-polar covalent bond for B. Whenever an element bonds to itself, okay? Draw the list out structures for water, ammonia, methane, hydroxide ion, and hydronium ion. These are three fairly simple examples. Assuming the octet rule is obeyed, how many covalent bonds will be formed in molecules for the following nonmetals? Well, you know, you should have this memorized by now. How many bonds does carbon form?
4.
4. How many does oxygen? 2. How many is fluorine? 1. How many is nitrogen? 3. What about helium?
6.
0. It's a noble gas. Okay? Kind of a trick question. Determine the formal charge of an oxygen atom in a hydronium ion. We'll do that next time. Name 4 elements that can expand their octets in compounds. So I think it's on the study guide, isn't it? Sulfur, phosphorus. You get the idea. Silicon. Which 2 compounds of nitrogen and oxygen do not follow the octet rule? I think it's on the study guide. NO and NO2. Write a compound for beryllium and boron that doesn't have a complete octet. So those are all pretty easy, the practice problems for chapter 9. But just a heads up, chapter 10 is busy. One thing about chapter 10, it crams 3 different theories into one chapter. One of them is valence shell electron pair repulsion theory. Next one is valence bond theory. And then the final one is molecular orbital theory. And so we have a lot to look at in chapter 10. Most of this stuff in chapter 9 on the study guide and the practice problems is pretty straightforward. Alrighty, any questions about any of this stuff?